In this video, we'll talk about using the method of partial fractions with irreducible quadratics. So in the last video, we had a method that worked for all rational functions with certain properties, right? This method could work if the denominator could be factored into linear factors, no linear factors repeated, and the degree of the numerator is less than the degree of the denominator. We had those three conditions that let us have the exact form of a over x minus 1 plus b over x minus 2, that sort of a thing that gave us partial fractions. What we're going to do is now go through each of these conditions and figure out if it doesn't happen, how do I fix the problem? So the first one we're going to look at is not all linear factors. So the point is, not all polynomials can be factored completely into linear factors. Right? The things you want to think about here are polynomials like x squared plus 1, or x squared plus 2x plus 5. There's no real numbers such that x squared plus 1 equals 0, which means there's no way I can write x squared plus 1 as something like x minus a1, x minus a2 for linear factors like that, because it doesn't factor. It's irreducible because it doesn't have any actual roots. So these also fall under the term of being irreducible. That's what we have to deal with here. These are polynomials where the discriminant in the quadratic formula is negative, and so it has no real roots, and that's a problem. But something that's nice about these things is that all polynomials can be factored into products of linear factors and irreducible quadratics. So once I take care of these quadratics, I'll handle every polynomial that I could ever imagine will be handled in one of those two places. That is, once we handle quadratics, we can handle linears and quadratics, and that will cover all polynomials, and therefore pretty much any rational function I would want to handle, I can use this method for. So how do we handle quadratics? Well, the main thing to think about is we're going to have terms of the form something like x plus 1 in the denominator. Now, the point here is the idea last time, and with all this stuff, has been the degree on top has to be less than the degree on the bottom, which if I have a bottom of x squared plus 1, that's degree 2, means my top can be at most degree 1, so something like ax plus b could be on top. It turns out I need both of these coefficients to make sure everything works out correctly in terms of the right number of variables in order to make my expressions line up on both sides of the equation. Right, from before when we had something like a over x plus 2, the point was that's degree 1 on the bottom. The only thing that can go on top is a constant. I don't have any more degrees to play with, but for quadratic terms, I need these two terms here. And again, this lines up with the fact that the degree on the bottom is 2, and I have two coefficients on top. Degree on the bottom is 1, I have one coefficient on top, and that's how it's going to be for all these different things. So in this case, to make a partial fraction work in this context, I need to have ax plus b on top for my irreducible quadratics. So the way to think about this is then every irreducible quadratic that shows up adds a term of the form ax plus b over that quadratic into the partial fraction decomposition. So that's our idea. We'll add those terms as well into our decomposition and then integrate from there. And the point is, I know how to integrate both of these terms, right? What I'm left with then, once I split this up, is something like an ax over x squared plus 1 and a b over x squared plus 1. And both of these I can integrate. This is a substitution, and this is an inverse tangent. And we'll see those show up in the example that we'll do here in a second. So let's work out this example here. 3x plus 4 over x minus 1, x squared plus 9. And so the point here is, what does my partial fraction decomposition look like? The first step is always find the form and then find the coefficients for the partial fraction decomposition. So my decomposition says I should have 3x plus 4 over the denominator equals a over x minus 1, and then plus this x squared plus 9 is an irreducible quadratic. It has no real roots. That gives me a bx plus c over x squared plus 9. We can then clear denominators like we've done for the past and get that we want 3x plus 4 equal to a times x squared plus 9 plus bx plus c times x minus 1. And one thing you'll notice here with these irreducible quadratics is that now it's not possible to clear away that a term by plugging in numbers, because there's no numbers that make x squared plus 9 equal to 0. So you're going to have to do your value substitution again, but it's going to be a little more involved because you're not going to be able to get rid of all the extra variables every time. You may still have to solve a system once you're done to get these coefficients. But let's see what we can get out of this. So we're going to start by plugging in x equals 1 because that'll get rid of the x minus 1 term, make this expression easier. So plugging in x equals 1, the left-hand side gives me a 7, And the right-hand side gives me an a times 10 plus 0. So a is 7 over 10. The next thing I'm going to plug in is 0, and this is usually a good idea on these sorts of problems, because if I plug in 0, it'll make this x go away, getting rid of the b from the sum as well. I can plug in 0. If I do that, the left-hand side gives me a 4. The right-hand side gives me an a times 9 plus a 0 plus c times a negative 1, which tells me that 4 is equal to 9 times 7 over 10 minus c. The 63 over 10, subtract that over, gives me a negative 23 over 10, which means that c must be 23 over 10. And now I have to plug in one more number, and I don't have any really nice and easy choices at this point, so I can plug in whatever I want. And so I'm going to plug in 2, because 2 will make the x minus 1 term go to 1, which is easy to handle. So I'm going to plug in 2. You can pick any number you wanted here, but I'm going to use 2. The left-hand side gives me 6 plus 4 is 10. This gives me an a times a 13 plus a 2b plus c times 1. And then I can just solve out for what I get here. 10 should be a is 7 over 10 times 13 plus a 2b plus 23 over 10. 13 times 7 is 91. And then we can solve out the rest of what this would look like in terms of being divided by 10. So I get a 114. Move that over, gives me a minus 14 over 10 on the left. So this tells me that b should be negative 7 over 10. So now we can write out our integral in this partial fraction decomposition and see where that gets us. So then from this, we get that the integral of 3x plus 4 over x minus 1, x squared plus 9 equals the integral of 7 over 10 over x minus 1 plus negative 7 over 10x plus 23 over 10 over x squared plus 9 dx. Now I'm going to split this here into 3 separate parts. I'll split the x term off of the constant term here. Now, let's work each of these 3 integrals separately. Integral 7 over 10 over x minus 1 dx. That one's pretty easy. That's just a log that we've had before. This is 7 over 10 log of x minus 1 plus c. For the second one, we have a negative 7 over 10 integral of x over x squared plus 9. For this, I want to do u substitution for x squared plus 9. So du is 2x dx. This then becomes negative 7 over 20 integral of 1 over u du, which becomes negative 7 over 20 of x squared plus 9 plus c. And now the last one is a 23 over 10 integral of 1 over x squared plus 9 dx. Now you could either do this with trig substitution or with using our formulas for inverse trig integrals to get to a 23 over 90 integral of 1 over x over 3 squared plus 1 dx by just pulling out a 9. I then want u to be x over 3, du is 1/3 dx, which means I get a 23 over 30 integral of 1 over u squared plus 1 du, which becomes a 23 over 30 inverse tangent of u plus c, and then I can combine these together to get my actual formula. So integral 3x plus 4 over x minus 1 x squared plus 9 is 7 over 10 log of x minus 1 minus 7 over 20 log of x squared plus 9 plus 23 over 30 inverse tangent of x over 3 plus c. So again, these integrals have many parts to them, but the idea is the same once you get going. And the new change here is the quadratic terms, but we can always split those into one term that has the x on top, and so is a u substitution, and the other one which doesn't, which becomes an inverse tangent integral problem. You're always going to see logs and inverse tangents showing up in these answers. This is how you get them using partial fractions with this sort of approach. But here's the idea of handling quadratics. If it's just a quadratic, you're going to split it up into 2 terms. The quadratic is going to have 2 constants on top, an ax plus a b. You have to solve for those coefficients as they go, and then you can split them up to do the integrals like you do here, and like you'll see in the practice problems as well. For doing partial fractions, even when they have a quadratic in your factorization.